Somewhere out in the ocean right now swims an animal heavier than any dinosaur that ever walked the earth, and its own tongue alone weighs about as much as a fully grown elephant. That animal is the blue whale, and the strange part is how late it showed up. Its ancestors spent millions of years staying fairly modest in size before something in the ocean changed everything. Food started gathering into dense, moving patches, and one whale lineage exploded upward until it became the largest creature the planet has ever produced. Here's the thing though, this wasn't evolution's first attempt at building a giant, not even close. Long before any whale existed, sauropod dinosaurs had already turned dry land into a world of slow-moving towers of muscle and bone. After those dinosaurs disappeared, mammals took their own turn at the same idea, producing mammoths, giant sloths, oversized rhinos, and marsupials the size of small cars. Completely different ancestors, separated by tens of millions of years, kept arriving at the exact same dangerous solution. So the real mystery isn't why a giant appeared once, it's why evolution keeps rebuilding the same experiment from scratch, again and again. Evolution itself has no goal in mind and no interest in being impressive. It only rewards whatever survives and reproduces slightly better than the competition in one particular place at one particular time. Depending on the environment, that winning strategy looks completely different from place to place. Sometimes speed wins, sometimes camouflage wins, and sometimes the answer is simply to become too big to kill. A larger body can overpower smaller rivals, shrug off hunger for longer, travel farther between meals, and scare off most predators just by existing. Once that advantage kicks in, later generations can keep drifting toward bigger bodies across millions of years, a long-term pattern some biologists call Cope's rule. That pattern isn't universal though. Plenty of lineages stay small, shrink back down, or vanish completely before the trend ever gets the chance to continue. Body size behaves more like a gamble than a climb up some ladder from tiny life to giants, shaped by food, climate, competition, anatomy, and sheer chance. That same gamble has played out in oceans, forests, grasslands, and entire prehistoric worlds that no longer exist, and every environment changes the odds while the underlying temptation stays the same. Predators think twice before attacking something that could crush them in one movement, and rivals lose access to food and territory the instant a heavier competitor shows up. Cold gets easier to survive too, since a large body loses heat more slowly, and hunger arrives later simply because there's more muscle and fat on hand to burn through. Long journeys get cheaper on top of that, because each kilogram of tissue in a big body actually runs more efficiently than the same kilogram would in a small one. Even digestion improves at large scale. A huge gut can keep low-quality plant matter fermenting for days at a time. That's essentially how an elephant survives on food that would starve a smaller animal with a faster metabolism, and how a whale can cross an entire ocean while feeding only during the richest weeks of the year. Size, in other words, creates options that smaller animals simply never get access to. Physics, though, starts collecting payment the moment an animal actually grows. When a body gets longer, its volume and weight climb much faster than the strength of the bones and muscles meant to hold it up. So a body twice as long ends up far more than twice as heavy. Bones have to thicken, muscles have to pull harder, and joints end up absorbing enormous new forces they never had to deal with before. Heat that used to be precious can suddenly turn dangerous to get rid of, and a fall that a small animal would barely notice can kill a giant outright. Reproduction usually slows down too, simply because bigger babies take longer to grow before they're ready to be born. Every increase in size forces changes across the entire body. Real gigantism means negotiating with dozens of separate limits at once, never adopting one clean, single adaptation. This is exactly why giant animals in movies rarely hold up to scrutiny. Enlarging a normal spider, wolf, or human without redesigning anything else would be a biological disaster. Limbs would buckle under the sudden extra weight, breathing would stop being efficient, and the whole body would likely overheat before it got anywhere at all. Real giants got there by having their entire bodies reconstructed around the problems that bigness creates, the same way you can't just stretch an image bigger without distorting it. Elephants stand on legs shaped like columns instead of bending like a cat's, and whales let the water carry their weight instead of fighting gravity directly. Sauropods, for their part, had bones reinforced exactly where the stress was worst and hollowed out everywhere else. Three completely different giants, solving the same physical puzzle with three completely different designs. A lineage can only grow as large as its inherited body plan actually allows, because evolution can't erase an animal and redesign a better one from a blank page. Every generation has to be built from parts that already exist. Sometimes an accidental feature becomes, millions of years later, the exact foundation a future giant needs, while another lineage reaches the same rich environment and simply lacks the anatomy to take advantage of it. Opportunity alone is never enough, either. Food has to be abundant, competition has to actually reward growing bigger, and the body has to remain mechanically possible all at the same time. The age of giant dinosaurs actually began with animals that weren't giant at all. The earliest relatives of sauropods were fairly small creatures wandering through the Triassic world. Over time, some of them shifted toward eating plants, growing longer necks, carrying heavier bodies, and walking on all four legs instead of two. Those changes did more than just make one dinosaur bigger. Together, they built an entire system capable of breaking the normal size ceiling for anything living on land. The most obvious piece of that system was the neck, which let a sauropod harvest a huge area of vegetation without ever dragging its enormous torso around to reach it. Energy that would otherwise go toward walking could instead go straight into near-constant feeding. High branches, low plants, and distant patches, all reachable from roughly the same spot. Strangely, the head at the end of that long neck stayed remarkably small, mostly because heavy chewing equipment would have been nearly impossible to support so far from the rest of the body. Sauropods solved that by mostly skipping chewing altogether, swallowing vegetation almost whole, and letting an enormous digestive system handle it deeper inside. That also meant the neck itself could keep growing longer without the head having to grow along with it. Feeding efficiency solved one problem, but breathing had to solve another, and the evidence suggests sauropods carried a bird-like respiratory system built around a network of air sacs. Air moving efficiently through the lungs could support an animal that was both highly active and growing at an unusually fast rate. Extensions of those same air sacs reached deep into the skeleton itself, hollowing out spaces inside the bones that cut weight dramatically without leaving the structure fragile. That's essentially how a sauropod's neck could grow enormous while staying lighter than a solid column of bone ever could. Even the feet may hide a piece of the puzzle. Soft tissue pads beneath the limbs likely spread pressure across the ground, sparing the bones above from dangerous extra stress. Legs built like straight pillars, meanwhile, kept the whole body upright using far less muscular effort than a crouched stance would ever need. Every one of these features made the others more useful. The long neck improved feeding, efficient lungs supported fast growth, and lighter bones kept the structural cost of it all under control. Egg-laying added one final advantage that mammals would later struggle to match. A female sauropod never had to carry one gigantic fetus all the way to term. She could lay an entire clutch of eggs instead, spreading the risk across many offspring at once. Most hatchlings almost certainly died young, but the ones that survived could then grow at genuinely extraordinary rates. Sauropod gigantism, in the end, came out of this whole cascade of adaptations working together, rather than from any single magical trait. Once sauropods crossed a certain size threshold, they reshaped the world around them. Adult animals became almost immune to ordinary predators, and their feeding altered entire forests and changed which plants could survive nearby. Young sauropods, though, still lived in a far more dangerous world, since a hatchling started out tiny compared to the giant it might eventually become. That gap was so extreme it effectively created two different ecological roles inside a single species. Juveniles had to feed, hide, and dodge predators in ways their own parents no longer needed to worry about. Growth itself, for a sauropod, became a kind of long journey through completely different worlds. Predatory dinosaurs discovered the same rewards of size, though their ceiling sat much lower than any herbivores, since a giant hunter could take on bigger prey through sheer force alone. Carnivores, however, only receive energy that has already passed through plants and the herbivores that ate them, and each step up that food chain loses a huge share of the energy available below it. That's why giant predators have always been rarer than the giant herbivores feeding them. A single landscape might support entire herds of enormous plant eaters, but only a handful of colossal hunters, which meant that when prey numbers dropped, the biggest carnivores tended to run out of options first. For more than 100 million years, dinosaurs kept exploring bigger and bigger forms, until an asteroid ended the entire experiment in what was, geologically speaking, an instant. Size had protected these giants from claws and teeth for millions of years, but it offered almost no defense against a collapsing planet. Forests burned, sunlight faded, and food webs fell apart, turning an enormous appetite into a fatal liability almost overnight. Small survivors could hide, eat less, breed faster, and simply endure conditions that giants never could. The world that emerged after the impact belonged to creatures that had spent the entire age of dinosaurs living quietly in their shadow. Mammals were among those survivors, and for most of the dinosaur era they had stayed fairly small themselves. Plenty of species were specialized and varied, but none came close to the size of the largest dinosaurs. After the extinction, roughly 66 million years ago, huge amounts of ecological space opened up across every continent. Empty roles sat waiting for new grazers, browsers, diggers, runners, and predators to fill them, and mammals expanded into almost all of it. The maximum size of a mammal shot up dramatically over the following tens of millions of years, a pattern that appeared independently across completely different regions and unrelated groups. Evolution was rebuilding giants all over again, just with an entirely different set of biological parts this time. Hoofed mammals produced huge browsers taller at the shoulder than a modern giraffe, and proboscideans gave rise to mammoths, mastodons, and a whole range of strange elephant relatives across several continents. South America raised ground sloths that could rear up higher than a grown human standing at full height. Australia, isolated from most of the world's placental mammals, produced its own set of enormous marsupials, and even rodents evolved into forms far bigger than anything from that group alive today. Each of these mammal giants was an entirely new answer to some very familiar pressures, built out of anatomy no dinosaur had ever had. Large herbivores could process tough plants, cover long distances between scattered resources, and resist most predators simply by being hard to bring down. Herd living sometimes amplified those advantages further, surrounding vulnerable young with a wall of adult bodies. Bigger brains and longer lifespans, meanwhile, let some species pass down knowledge about water sources, migration routes, and seasonal danger. Even so, mammals never quite matched the greatest sauropods, and part of the reason may simply be the different biological package they were stuck with. Pregnancy forces a mammal mother to carry her growing offspring inside her own body for months, and milk then demands a long stretch of costly energy after birth. Larger species generally mature slowly and produce far fewer young as a result, so a population of giant mammals replaces itself at a genuinely risky pace. Mammalian metabolism also generates a lot of internal heat that only gets harder to release as an animal grows larger, and on land, every extra kilogram still has to be held up against gravity with no help from anything else. No single limit explains the entire gap between mammals and sauropods, but reproduction, anatomy, metabolism, food, and available space likely combined to create a genuinely lower ceiling. Even so, mammals still pushed close enough to that ceiling to reshape entire continents on their own. Then, toward the end of the last ice age, many of those giants vanished within a surprisingly short window of time, as climate shifted quickly and human hunters spread into new territory at exactly the same moment. Researchers still argue over how much blame belongs to each factor in different parts of the world, but the overall global pattern is impossible to miss. Mammoths, giant sloths, huge kangaroos, and dozens of other massive animals simply disappeared, one after another. Once again, the biggest bodies had been powerful during stable times and painfully vulnerable the moment things fell apart. One branch of mammals, though, managed to escape most of the limits that land imposes by walking back into the water. What followed was a transformation far more extreme than simple growth. Legs turned into flippers, nostrils migrated toward the top of the skull, and tails became the main engine for movement. The whole body reshaped itself into something streamlined, all while keeping warm blood, live birth, and milk. The core mammalian package, fully intact underneath. Water solved one of the harshest problems land had ever created, because buoyancy could support a mass that would have crushed any set of legs trying to hold it up on solid ground. The ocean, though, introduced a brand new problem of its own. Water pulls heat away from a body far faster than air ever does. A small aquatic mammal has to burn a huge amount of energy just to stay warm, but a larger body loses proportionally less heat than a smaller one. In cold seas, being big essentially works as a form of insulation, an effect that thick layers of blubber reinforce even further, while also storing fuel for long migrations. Returning to the water, in other words, pushed marine mammals away from the smallest possible body sizes and opened a path toward dimensions their land relatives could never have reached. Early whales didn't jump straight to blue whale proportions, though. Many stayed fairly moderate in size for millions of years despite living entirely at sea. Baleen whales eventually developed a completely different feeding strategy, replacing teeth with keratin plates that could filter enormous quantities of tiny prey straight out of seawater. Even that innovation, though, didn't instantly produce record-breaking bodies. The real leap in size seems to have happened much more recently, over the last several million years, as ocean currents and climate patterns grew steadily more variable. Productive waters began concentrating krill and small fish into dense, seasonal patches instead of spreading them evenly across the sea. Food started arriving in short, temporary explosions separated by huge stretches of nearly empty ocean, and that kind of world rewards animals that can travel far and eat enormous amounts very quickly. Larger whales could store more energy between these feeding grounds and move more efficiently over long migrations. A single giant mouth could also engulf an almost unbelievable volume of prey-packed water in one attack, turning every dense patch into a short-lived jackpot of energy. Several different lineages of baleen whale appear to have grown large independently, all under roughly the same new ocean conditions. Similar ocean pressures simply pushed different whale branches toward the same extreme result again and again, rather than gigantism spreading down from one single ancient super whale. The blue whale became the most extreme version of that trend, and its size lets it feed with incredible efficiency, but only when prey density is high enough to justify the effort. During a lunge, the whale accelerates hard and opens a mouth that expands almost like a parachute, letting water and prey rush into a throat pouch that can swell around an enormous load. It then forces all that water back out through its baleen plates and swallows whatever solid food remains. Every single lunge costs a significant amount of energy, since the whole body slows down dramatically under the force of everything it just swallowed. A poorly timed lunge can actually burn more fuel than it earns, which means gigantism only works here because prey happens to be concentrated enough, often enough, to repay that enormous cost. That narrow requirement may explain why blue whales are enormous, but not somehow endlessly larger. The ocean can only support a body this size, while food keeps arriving in dense, reasonably predictable bursts, and even a body fully supported by water eventually runs into hard physiological limits of its own. The blue whale, then, represents both a triumph and a warning at the same time. Evolution found a way to build the largest animal it has ever produced, but only inside a fairly narrow ecological bargain. Break up the prey patches, disrupt the migration routes, or slow reproduction even slightly, and that bargain starts to fail, a vulnerability that follows almost every giant throughout history. Large animals need more territory, more food, and more time to recover from any losses, and their populations tend to contain far fewer individuals than populations of smaller species. A drought, a cooling event, a habitat collapse, or a new predator can hit them disproportionately hard, and because reproduction is so slow, every single death effectively erases years of future growth. Humans made that danger even worse, since large animals tend to be visible, valuable, and painfully slow to replace. A hunter doesn't need to kill every last individual to push a fragile population into decline, and roads, farms, ships, noise, and fragmented habitat can keep applying pressure long after any direct hunting stops. Many of today's giants only survive because ongoing conservation work is actively holding the last pieces of their world together, which can make sheer bigness look, from the outside, like the final achievement of evolution. The fossil record tells a very different story, though. Small bodies dominate nearly every branch of life because they're cheaper to run, faster to reproduce, and far more flexible when conditions change. Giants only show up when unusual circumstances make their much higher costs worth paying, and they flourish exactly as long as food, climate, anatomy, and geography all happen to stay aligned. The moment that alignment breaks, size can flip from an advantage into a trap almost overnight. That's the twist hiding inside every age of giants. Evolution builds enormous animals only when certain temporary worlds happen to reward extreme specialization, not because bigness is some universal winning strategy. Sauropods were built for landscapes rich enough to support moving towers of muscle, and mammalian megafauna rose when empty continents offered open space and abundant plants. Baleen whales, meanwhile, expanded once the ocean started gathering tiny prey into colossal seasonal feasts. Each giant, in its own way, became a physical record of the world that made it possible, preserving the terms of that world inside its bones, lungs, and reproductive strategy. The moment those terms changed, the largest bodies were usually the first ones to feel it. Nature's experiments with gigantism, then, were never really just stories about size. They reveal how life turns a fleeting opportunity into anatomy. They show how the very features that create strength can also be the ones that create fragility. Most importantly, they prove that evolution has no permanent winners, not even the blue whale. It may well be the greatest giant life has ever built, but its existence doesn't mean evolution has finally reached some kind of finish line. It just means that, for one brief window in Earth's long history, conditions in the ocean happened to make a body like that possible. Somewhere down the line, those conditions could easily vanish, and this current age of giants could quietly close, just like everyone before it. But if some future world ever rewards bigness again, evolution will start the whole experiment from scratch. Different bones thickening, different lungs adapting, some new body plan slowly edging toward the limit all over again. Giants keep reappearing throughout history for one simple reason: the temptation of size never really goes away. They keep disappearing for an equally simple reason: sooner or later, no advantage can outrun a planet that refuses to stop changing.